I just wanted to add to the question of what was going on with the astronomers at this time, and maybe put some of this in perspective. It's a real pleasure to be in front of people who actually know something about the history of physics. But anyway, how do I do this? Okay, so we'll start. Where black holes begin is the discovery of the existence of horizons in relativistic solutions. I just want to point out that although there's a lot of literature on what happened in 1916, 1917, and the fact that Drost, in fact, in his thesis, which was with Lorentz and consequently well-informed on the work on relativity that was going on with Einstein, had already started in a year before working on a solution based on the Entwerp paper. And in 1916, after Schwarzschild had presented a result at the Royal Netherlands Academy showing the same solution, what I want to emphasize is the problem these guys were looking at was a purely dynamical problem. It wasn't the general question of what is the structure of a gravitational field, it's what's the force law that results from general relativity, and how does this fit into a field of research which was extremely well developed at the end of the 19th century. It's called celestial mechanics. One of the things that I, in fact, find most interesting is that if you go through the early papers, virtually everybody who was involved with the early work on relativity, especially the external solution for a point source, all of these people were celestial mechanicians. They knew perturbation theory, they knew how to deal with gravitational potentials, they didn't have to ask the rather delicate question of what does the interior of this thing look like. All they had to do was say, we're far enough away that we can treat it like a point source, that's it. Okay? And so, in fact, this is, I think, really the reason why when Einstein said to Schwarzschild upon receiving the postcard that explained, I have this result, and of course they knew each other very well, there was the reaction that I was actually surprised, Einstein said, it came so quickly. The thing that's important about this paper is that it was actually inspired by the fact that Einstein's solution for the precession problem was not complete. It was only a perturbation expansion. And in this case, because you can write out a very simple Lagrangian based on a generalized metric, and it's a nice symmetric solution, you can do it in a coordinate system that everybody understood, you can immediately calculate the Christoffel symbols and also the curvature tensor, and you don't have to know what the hell this means physically. All you have to do is approach this essentially as the classic problem that had been well explored in the second half of the 19th century, namely arbitrary distributions of masses. Now, the thing that's, I think, interesting from the astrophysical view is that the next paper, which doesn't have a complete solution and puzzled Schwarzschild tremendously, is the interior problem. And the fact is, the interior problem is posed in a context which is kind of unusual when you consider what was going on at the time. There was a controversy beginning around the beginning of the 20th century over whether stars are compressible or not. I know for those in the audience who don't have this color hair, this seems like a very miserable and technical problem, but in fact there was a very serious problem in how to apply the gas laws to something which is self-gravitating. And the Lane-Emden equation, which is really popularized by Emden's book, was only in 1908. So people were still arguing how to treat the interior structures of stars from the point of view of gas laws and thermodynamics. And at the same time, on the other side of the English Channel, Jeans and Eddington were beginning to deal with radiative problems. So this was a first attempt to find the interior solution within the context of relativity as a modification of the Poisson equation. It was a logical extension Unfortunately, that was the next step for Schwarzschild. And this is just 1 century old. This is from Göttingen. Okay, so from this point of view, one of the things that I also find interesting is that Schwarzschild, among all of the people who were involved, was the one person who knew what stellar atmospheres were. He had a very clear idea of what kinds of observational tests you would be able to have for anything in the interior of stars, because he was the first one to successfully calculate the transfer of radiation through an atmosphere with lines. He was the one who worked out the calcium lines in the solar atmosphere. And so he was thinking about things in terms of photons, but the other people whose names keep coming up here, like Chibita, De Sitter, Lawrence, Eddington. Eddington, you may know, was trained as an astronomer. That his first book was The Motion of the Stars in Space, which was basically his thesis. And so he was perfectly in tune with the techniques of classical data analysis, and all of these people were very familiar with orbits. And so to them, it didn't matter what the structure of the space was. They knew what a geodesic was, they knew what closed orbits meant, they knew what precession meant. I should also add that De Sitter in particular was extremely well known in the astronomical community because of his work on the satellites of Jupiter, which is a very difficult perturbation problem when you consider what the available resources were at the time. The other thing that's important about relativity at this point is that the techniques that Einstein was proposing and that were available to test relativity on the cosmic scale were essentially unchanged from the eclipse expedition to measure the expedition to measure the transit of Venus. These were classical methods. They could be done, in this case, with photographic plates, not with sextants or quadrants. And so the accuracy could be much higher, but they really involved no more technology than good lenses, good telescopes, and good measuring machines. Okay, so there was no great technological conceptual leap that was necessary at this point. So just to summarize it, you had a new force law. There were, Schwarzschild himself had actually introduced questions of the topology of the universe on large scale, but he considered these largely speculations. Einstein was beginning to ask cosmological questions within a year of Schwarzschild's death, the paper on the cosmological considerations that involved the implications for the cosmological constant and Mach's principle were all introduced within 1 year. And then there was this question of the final state. Now, this is to come back to the previous talk and to emphasize this. The final state isn't the question when you have an incompressible mass. It doesn't matter. There was no stellar evolution. Eddington, for example, in dealing with the compression problem, and Jeans in the 20s in astronomy and cosmogony, the stuff that had been done on tidal equilibrium figures by everybody from Poincaré, Riemann, and Roche, all the way through Jeans, all of that was done with liquid drops. The equation of state being incompressible, you could very easily solve the Poisson equation, and then you were using these to get the potential of the outside structure. But these were purely barotropic models. They had no evolution because they had no internal structure that was going to change. Eddington, following people like Schwarzschild, was beginning to ask about radiative transfer issues. So it wasn't simply that these things were cooling and getting darker, it's that as you change the temperature and density in compressible stars, you change the opacity. This was one of the big advances in Eddington's book on the internal constitution of the stars, the introduction of quantum theory for the calculation of the radiative transfer problem in stellar interiors. Now, this is what makes the centers so dense and so hot, that you have to solve simultaneously temperature gradients which are not adiabatic. So you can't any longer use the simple application of a polytrope. For those who don't know, a polytrope is a simple equation of state in which the pressure is just a function of the density. And so the equation of structure is exactly the same as the Poisson equation. It's a one-parameter problem. Now, in the normal ideal gas, we all learn in childhood that you have a density to the 5/3 for a monotonic ideal gas. One of the things that Chandrasekhar found, just as a side comment, was that if you go to a relativistic gas, the equation of state softens. It goes to rho to the 4/3, which happens to be the same thing as a radiation-supported star, which was Eddington's standard model. And so you knew exactly what the relation was between the radius and the mass. This is the reason why people were so interested in polytropes. Now, with the introduction of opacity, you suddenly had this additional point. Okay, this is just a pedagogical thing. Okay, let me stick to the slides and try not to make too many side comments. There was a research divide here, and it wasn't just between the mathematicians and the physicists and the astronomers. The astronomers did have an idea of what relativity meant. They certainly knew special relativity, and especially the Americans had a long tradition of the application of celestial mechanics to even the new quantum mechanics. I'm sorry, the new quantum theory, as it was at the time. And so it was very easy for them to understand the implications on a local scale. It was the global scale that they didn't really have. They were very interested in questions like Mach's principle, largely because it was getting to some fundamental issues. But otherwise, these were basically the dividing lines. Now, I wanted to point out also that there were pedagogical differences. That after the war, and I'll concentrate on the period now after the war because that's when the observations really began, those who were propagandizing for relativity in general were people like McVitie, who had come from traditional astronomy. McVitie was actually, again, a celestial mechanician. He taught a course on mathematical astronomy and mathematical statistics at Illinois, and he was one who, in a popular magazine, Sky and Telescope, which was like Stern and Weltraum or the Stella, was very, very widely read. Struve also wrote for this, and some of the most important astronomers of the post-war period wrote for it. And he propagandized with this article, Why Should Astronomers Study Relativity? He didn't mean special relativity. And this was already in the mid-1950s. The teaching of relativity through the early 60s was either from the cosmological side, with the exception of Tolman's book on relativity, thermodynamics, and cosmology, which was sort of an attempt to merge everything. Bergman's book was hardly used. It was one you read, you knew that somebody had hidden it in the library, but this was Einstein's view spoken through Bergman of how you should approach the mathematical side of relativity. McVitie wrote a book that went through 2 editions, 10 years apart, which emphasized cosmology. Adler, Bazin, and Schiffer emphasized cosmology. Landau and Lifshitz emphasized gravity as a field theory. This was very general. The Schwarzschild solution was shown. People talked about gravitational collapse. There were references to the Oppenheimer and Snyder work. There were even references to Harrison, Thorne, Locano, and Wheeler in some of these books. But in general, the one thing that was important was these didn't talk about the astronomical implications at the stellar level. They were all talking about things in cosmology. Relativity, when it was taught in the late 60s and early 70s, in most, at least American and also many European universities, was largely geared toward cosmology. So, I think the best study that's been done about singularities and why I'm not talking about that in particular is this one by Ehrman and Eisenstadt. But there are a lot of references here, largely for those who might want to read this later. But I'll just point out that when Eddington wrote the version of what became the Eddington-Finkelstein coordinate system, which was the first one to actually confront what a horizon is, at least what an event horizon is. He was doing that in the context of criticizing Whitehead's theory of gravitation. So it was just a short note in Nature, and it really wasn't either well known or taken very seriously. And as these guys point out, he didn't take it seriously enough to even include it in the second edition of his book, Mathematical Theory of Relativity. The next solution was the one that you could say was the taming of the singularity. It was the extension to the complete manifold of the field of the Schwarzschild solution, and recognizing that in fact the 2M, that is the so-called, at the time, Schwarzschild singularity, was nothing but an event horizon. Fonsfeld wrote a paper in PhysRev just before Kruskal and actually references that in the note added in proof. But the point is, you see that it was kind of in the air, that by the early 1960s and late 1950s, it was recognized that there was something going on here, that this wasn't a breakdown of the theory, it was an observational thing, that the horizon actually had a meaning, but it was an event horizon. And Rindler had also clarified this in the cosmological context by emphasizing the difference between particle and event horizons in finite cosmologies. And then the Kerr solution came out, apparently out of nowhere, except people had been talking about rotation and relativity going back to the Lenz-Turing paper in 1918. So the really important thing I would like to just overlap here with the previous talk is that there was a mention at the first Texas Symposium by Kerr of the solution. So astronomers who were reading the proceedings of the first Texas Symposium and not reading PhysRev letters found out about this because it was in the same session as discussions of neutron stars and relativity. I can't emphasize how important this paper is. And no, this is not brown nosing. This really is a beautiful piece of work. And this is why I don't have to talk about any more of this, except to point out that Chandra's major contribution to the astrophysical side of things was really this book, The Principles of Stellar Structure, which kind of put all of this in context. This is the first book in which evolution starts to appear. Eddington's book, while it talked about the formation of stars, the last chapters on the interstellar medium, it was clear that stars form. There's really no discussion in that book of how stars die. This, on the other hand, emphasized as an added comment that nuclear energy was important in the evolution of stars and pointed back to the internal structure problem as something that would be driving evolution. Okay? This is the one that we can call naming the singularity. Oh dear. I'll talk quickly. This is the, sorry. This is the everything but the kitchen sink thrown into a black hole. This probably did more, not just to popularize the idea of a black hole, but to serve as the equivalent in astrophysics of a Feynman diagram, in the way that it was said that that brought quantum electrodynamics and field theory to the people. This is the one that allowed people finally to understand that a black hole, the Kruskal solution, is just an event horizon. Now, okay, very quickly, there was another side to all of this that was pointing to relativistic astrophysics, and especially the paper by Seifert in 1943 that pointed to a group of galaxies, ordinary galaxies, which were known to have distances and redshifts that were not enormous. These were not quasars as we now know them. These were systems that were ordinary galaxies, except they had star-like nuclei, which meant a few arc-seconds across. Siebert was one of the few who could work on these because he was at Mount Wilson at the time and was able to take decent spectra and actually calibrate those spectra. And this is the first example that I know of in the literature of the line profiles of the permitted and the forbidden lines. That is, lines that look like planetary nebulae, so very low density gas, very highly ionized, indicating that the central sources had to have the equivalent color temperatures of over 30 or 40,000 degrees. Things that look like white dwarfs that people knew were the centers of planetary nebulae, and yet, in this case, the damn things were as large as the nucleus of a galaxy. And these velocities are thousands of kilometers per second. You can see from the points, these are well-resolved profiles. This is extremely important because it doesn't matter what the energetics are here. This is just straight dynamics. Astronomers knew how to deal with this. And within this kind of fell through the cracks because, with the exception of Mount Wilson, there weren't any telescopes of sufficient size or spectrographs of sufficient sensitivity until after the war. The development of photographic plates and photoelectric astronomy was extremely important in the post-war period. And especially in the 1950s, Vulture was the first one to deal with the polarization of the Crab Nebula at the same time as Shklovsky was saying that the radiation was synchrotron. So again, this was in the air. And in this paper by Vulture, he, for the first time, pointed out that there's something relativistic in the center of these Seyfert galaxies. And he did this without knowing their exact distances, without knowing what the energy distributions were. It was pure dynamics. These lines are forbidden lines. They are formed optically thin. You don't have to worry about radiative transfer. You see all the gas that's there. And if these lines are at least a few hundreds of kilometers per second, it doesn't mean that you can have anything but a relativistic object. Okay, there were several suggestions at around the same time. These were discussed mostly in the second Texas Symposium. And okay, I'm sorry that this is going too long. The problem really was that if you were going to look for black holes, or if you were going to look for neutron stars, you either looked for supernovae, or you had to look for something that would evolve toward that state. Stellar evolution calculations didn't begin until the 1950s. Nobody really knew what would happen to a star when this nucleosynthesis was going on. And so the idea that a star expands as it's first evolving was something new in the 1950s, and Martin Schwarzschild and Fred Hoyle and Alan Sandage, who later played roles in virtually all of astrophysics of the late 20th century, were in this. The realization that stars have a mass function that goes from about 0.1 solar masses, perhaps over 60 or 70 solar masses, the fact that binary stars of 50 solar masses each of the components were already known by the 1940s. So all of that was in place, but the problem was nobody still knew how to look at the final states of these systems. The first paper to use things like the Roche limit, the idea of exchanging mass between stars because they've reached a tidal limit, was again coming from the celestial mechanics community. Kuiper was a celestial mechanician. That's why he knew what the Roche solution was. And this was the way that you described stars that were filling this surface, okay, filling the tidal surfaces. People had done tides for liquid drops, so there was no problem here. But the problem was, what would happen if a star was constrained because it had a companion? That is something that happened after the second Texas Symposium. That was the late 1960s, and the names that I've listed here, Kippenhahn, who's in Germany, Plavec in Czech Republic, Paczynski in Poland, Kopal. I've left out a couple of other people who were working on this. But binary star work was something that was very different than ordinary single stars, because the whole point is if the stars are close enough, there's a limit the radius can't get larger than the tidal limit, or material starts to flow. That was a very important realization. The last one, I'm sorry this is so many words, but the realization was that classical novae were compact binaries with periods of a half day or less. That was the major step in recognizing that something relativistic could happen, because these were systems that had disks, they had instabilities, they eclipsed, you knew their masses, you knew there was a white dwarf with a normal star next to it, and material was piling onto the white dwarf from the companion. That was known by the mid-1960s. And so the last one, this point, the first example I know of gravitational waves in astrophysics was the paper on W.Z. Szigeti, in which Greenstein and company, and actually others following, suggested that you would have to evolve this system, which had a period of only a few hours. Okay, 2 stars at that time of a solar mass or so, with a period of only a couple of hours, had never been seen before. So this system was so short period that they figured the evolution might actually be maintaining contact with the Roche surface by gravitational wave emission. Okay, the last point was that this immediately led to people talking, it's an event horizon, right? So time expands. So the discovery of X-ray sources outside the solar system, this had been also thought of for neutron stars as early as 1960. There were calculations of the X-ray emission from those after the supernova. The second was the paper by the NRL group, Friedman and company, who had mostly been working on the sun, but also found these 2 point sources, one of which was in Scorpius, and then the identification by Sandage of SCO-X1. The suggestion by Zeldovich and company, and also by Trimble and Thorne, that binary stars, massive binaries, would be a way of looking for black holes, or at least looking for what they call dark compact objects. And a paper by Wheeler, which is very under-referenced, but was in annual reviews. I should point out that there's a sociological aspect here, because Burbage was one of the editors. And so there was a thrust to get papers on relativistic problems in the annual reviews very, very early, largely because of the editorial board. Then came the discovery of this one source, and I'll finish with this, Cygnus X1. This was first identified as an X-ray source, then it was shown as a radio source, and radio measurements, and this is important because radio interferometry was in its early years at this point, multiple element radio interferometers, identified the position to 3 arcseconds. This was the first time that you had a radio source, a variable X-ray source, and an optical identification, all within the space of 1 year. And within a year, that velocity curve showed up. This is an amplitude of roughly 100 kilometers per second. This curve is a stellar spectrum. It is an OB star, and this curve is the emission lines in antiphase. And so it was clear you could get the mass ratio here. This was Bolton's result. This is the appearance of a black hole, the first direct observation. The mass has to be greater than 4 solar masses. And in fact, was suggested as being 7. And there was nothing known at the time in any equation of state that would allow you to get more than 3 solar masses. Plus, the most important thing that Zeldovich had already used as an argument for SCO-X1, the emission line here is helium-2, which meant you had a very compact object. And so you had an accretion disk, you had a binary system with a period of roughly 5 days, and a large velocity amplitude. And the rest, I'll just say, the last step was figuring out what the structure of the accretion disk would be. And if any of you want, just download the presentation. Again, thank you for your patience.